everybody. It's always a pleasure to have you in this class, and today we are going to be talking about dimensional analysis. Dimensional analysis is a procedure that will help you to know if what you're writing is correct. Let me put it this way. AP Physics 1 is designed in such a way that requires a deep conceptual understanding of the core concepts in physics. Do you understand? It requires a deep conceptual understanding of the core concept in physics. As a result, the questions have been designed so that very little numbers are used, just algebra. But then, if it's all algebra, how do you know that what you have written is correct? Without numbers, the only thing that can save you is dimensions. There are 4 major objectives of this lesson. In other words, by the end of this class, you should be able to define a physical quantity and state the dimensions. 2, be able to explain the meaning of the dimension of a physical quantity. 3, be able to calculate the dimensions of a physical quantity. And 4, which is the most important, be able to apply the method or principle of dimensional analysis in solving physics problems. If you understand these concepts, it will help you a lot in this class. Now, we have already laid down the foundation for this class, so I'm going to rapidly go over some of the things you need in order to understand the concepts we will study today. And the first is the concept of physical quantities. Physics, as you already know it, is a quantitative science. It's both a quantitative and an empirical science. It's empirical in the sense that it relies on observation and experimentation. In order for us to experiment, we have to measure. In other words, experimentation implies measurement. And anything that can be measured is a physical quantity. Any attribute of nature that can be measured is a physical quantity. Similarly, physics being a quantitative science implies that physics deals with quantities that can be measured. Anything that is measurable is quantifiable. Anything that is measurable is quantifiable. Understand that. If it cannot be measured, it is not science. Let me put it that way. If it cannot be measured, it is not science. When we talk about measurements, we mean comparing a physical quantity with a precisely defined standard. It means comparing a physical quantity with a precisely defined standard. That standard upon which a given physical quantity is compared with is called the unit. Now, the reason I'm stressing this is because there is so much confusion in textbooks, in the internet, as well as with videos on YouTube about units and dimensions. They use them interchangeably, and they're not. Units are different and dimensions are totally different. And therefore, you should be aware and you should be able to distinguish units from dimensions. Okay, to give you the difference, I'm going to use a simple example. Take you, for example. You have a name. If I call that name, you will walk up here. And only you will walk up here because that name identifies you. Is that clear? But then yesterday you wore something different. Today you are wearing something different. Even though you wore different dresses, you are still called by that name. So what you wear is like units, and what you are called is what? Your dimensions. Do you understand me? It doesn't matter what you wear, your name stays the same. Now, the dress you wear depends on the circumstance. The unit used to measure a given physical quantity depends on what? The circumstance. For example, if we are measuring the distance from the Earth to the Sun, it is just wise to use kilometers. But if you are measuring the diameter of an atom, it is just wise to use what? Nanometers. If you are measuring the duration of the Earth, it is wise to use what? Centuries or years. But if you are measured the time it takes for a click or for me to produce a sound, it is wise to use what? Seconds. Therefore, the units employed depends on the particular what? Context and circumstance, but irrespective of the units used to measure a given physical quantity, the dimensions always stay the same. That is a profound statement, and I'd like for you to write it down in red. Irrespective of the unit used to measure a given physical quantity, the dimensions always stay the same. The dimensions always stay the same. Irrespective of the unit used to measure a given physical quantity, the dimensions always will remain the same. In other words, the dimensions of a physical quantity, listen attentively, fellas, the dimensions of a physical quantity denotes the physical nature of that quantity. If I were you, I'll write that statement down. The dimensions of a physical quantity denotes the physical nature of that quantity and does not change irrespective of the unit used to measure that given physical quantity. Now, the next thing you need to keep in mind, is the fact that the dimensions of a given physical quantity will tell us how that given quantity is related to fundamental quantities. Will tell us how that given quantity is related to fundamental quantity. You will realize the importance of this statement very soon. Remember, I have likened dimensions to be like your name and what you wear on a particular day to be like the unit used to identify you. Are we together? Which means irrespective of what you wear, your name will stay the same. If you are going to a party, you will dress in a party clothes. Your unit changes. If you are going into a business meeting, you are dressed in a business attire. Your unit changes. But in all the circumstances, your name remains the same. Now, the very last statement I asked you to write down was the fact that the dimensions of a physical quantity shows us how that quantity is related to what? Fundamental quantities. What do I mean by that statement? There are two implications of that statement. One, it means that fundamental quantities already have preset dimensions. And before we proceed, it is important for you to know that the dimensions of a physical quantity is represented by what? Square brackets. So if I put Johnny in a square bracket, what this means is this represents the dimensions of what? Of Johnny. So if I put here V, this represents what? The dimensions of V. Each fundamental physical quantity has a representative dimension. So, for example, the dimension of length is capital L. The dimension of time is capital T. The dimension of mass is capital M. The dimension of current, electricity, is capital A. These are the four base quantities upon which all other quantities in this course will be expressed in terms of. Let me say that again. In AP Physics 1, we will be able to express all physical quantities in terms of these four quantities. If we have the physical quantity velocity, velocity is defined as change in displacement, displacement over time taken. What this means is that the dimension of velocity is equal to the dimension of what? Displacement divided by the dimensions of time. Displacement is distance, and distance is a length. Therefore, the dimension of velocity is going to be equal to the dimension of length over the dimension of what? Time. This is equal to LT minus 1. It's equal to LT minus 1. Let's look at another example again. Acceleration, A, is defined as change in velocity divided by change in time. This implies that the dimensions of acceleration is equal to the dimensions of what? Change in velocity divided by change in time. In other words, the dimensions of acceleration is equivalent to the dimensions of what? Velocity divided by the dimensions of time. So A, the dimensions of velocity is LT minus 1 divided by the dimensions of time, which is just t. This is going to be equal to LT minus 2. Force F is defined as mass times acceleration, which implies that the dimensions of force is equal to the dimensions of mass multiplied by the dimensions of what? Acceleration. Therefore, the dimensions of force is equal to what? The dimensions of mass is capital M. The dimensions of acceleration is LT minus 2. This gives you the dimensions of what? Force. Let me do another example again. Density rho is equal to defined as mass over what? Volume. This means that the dimensions of density is equal to the dimensions of mass divided by the dimensions of what? Volume. Therefore, the dimensions of density will be equal to what? Capital M. What is volume? Length times width times height, which is going to be L cubed. Hence, the dimensions of density is going to be equal to capital M L negative 3. I need for you guys to do this. 1, calculate the dimensions of work. Work, capital W, is force multiplied by distance. 2, power, capital P, is force multiplied by velocity. 3, momentum, work in your groups, is mass times velocity. 4, pressure, which is force over area. So work in your groups and do this. You have 5 minutes to finish this. All right, thank you, everybody. Let's do this. The dimension for work is equal to the dimension of what? Force multiplied by the dimension for distance. The dimension for force is MLT minus 2. Distance is L, so this will be what? ML squared T minus 2. Now, what was the next quantity? Power. The dimension for power will be equal to the dimensions of force multiplied by the dimensions of V. So this is MLT minus 2. This is LT minus 1. And when you simplify, this will be ML squared T minus 3. We have pressure. The dimension of pressure is equal to the dimension of force divided by the dimension of area. So this is MLT minus 2 divided by L squared, which is going to be ML minus 1 T minus 2. The dimension of momentum is equal to the dimensions of mass multiplied by the dimensions of velocity. So this is going to be capital M L T minus 1. So these are the dimensions of the quantities as indicated on the board. If you have not understood, please let me know before I proceed to the next section. Yes, please. Pressure is capital P, power is capital P, and momentum is small p. It's just a matter of convention. Yes, please. They will indicate, they'll tell you. They'll tell you, yeah. It wouldn't make sense if they don't. The last thing for today that we are going to do, which is the most important, is the principle of dimensional consistency. Is the principle of dimensional consistency. It's the principle of dimensional consistency. Now, it is important for you to know that in order for you to add or subtract or equate anything in science, they must fulfill the following condition. Let me put it this way. We can only, write with me, add, comma, subtract, or equate two or more terms with the same units or the same dimensions. We can only add, subtract, equate two or more terms with the same units or with the same dimensions. This is a very profound statement. And I would like for you to write it down in red if you have not written it down. If you have written the statement down, highlight the statement. Take, for example, stop what you're doing, please, and concentrate here. Take, for example, if we have 3 meters plus 3 or 2 centimeters, this is super inaccurate. We cannot do this in physics, even though they have the same dimensions. You cannot add two numbers with different units. Do you understand me? If you have 3 kilometers or 3 kilograms plus 2 kilograms equal to 5 meters, this could not happen because the units are what? Different. Do you understand that? The units are different. So you can only add, subtract, or equate two or more terms with the same units or with the same what? Dimensions. It's possible for two or more terms to have the same units and dimensions, but not always. Let me give you an example. 3 meters and 3 centimeters, they have what? Different units, but they do have the same dimensions. The same dimensions of what? Length, but they do have what? Different units. You understand that, right? The unit here is the meter, the unit here is what? Centimeter. But all of this represent a length, and this represent what? A length. And as long as it represents a length, its dimension is what? L. So it's possible for two things to have the same dimensions but different units. Now, let's take a look at another example. 5 kilograms and 5 kilograms. They do have the same dimensions and the same what? Units. Are we together? They have the same dimensions and the same unit. This is equal to that. But if we have 5 kilograms and 4 kilograms, they have the same unit and dimensions. They have the same unit and dimensions. But can we equate the two? No. because they have different what? Magnitudes. Do you understand that? They have different magnitudes. Therefore, it is critical for you to understand the following facts. For an equation to be correct in science, for an equation to be consistent, it must obey the following property. One, all the additive terms, listen carefully, all the additive terms must have the same units or the same dimensions. This is a consequence of our previous statement. And this is the principle of dimensional homogeneity. Therefore, all equations, write this down, all equations that you will write down must be dimensionally consistent. All equations that you will write down must be dimensionally consistent. All equations that you will write down have to be dimensionally consistent. There is no shortcut. By that I mean the dimensions of all additive terms must be the same, or the units of all additive terms must be the same. Do you understand me? Let me demonstrate what I mean by that. If I give you, for example, an equation, let me write down two equations. One, x equal to x naught plus v naught t plus half a t squared. This is equation 1. And let me write down another equation. Half mv squared equal to fx plus half gh. This is equation 2. Let us find out which of the two equations is correct. And how can we do that? Remember, I told you in the beginning of the lesson that when you are dealing with an algebraic equation, what do? You check for dimensions. When numbers are substituted, you check for what? Units. When you are dealing with an algebraic equation, you check for dimensions. When numbers are substituted, you check for units. I'd like for you to say that statement with me. Please, go on. Repeat that statement. When you are dealing with an algebraic equation, you check for dimensions. Everybody.
When you're dealing with an algebraic equation, you dimension.
Now again and louder.
When you're dealing with algebraic equations, you check for.
But when numbers are substituted, what do? You check for? Units. You check for units. I could not overemphasize the importance of that statement. Yes, we are in kindergarten and we are learning physics. Let me demonstrate how to use this here. If this equation is correct, then what that means is the dimensions of all of these terms added and equated together must be the same, right? This is distance, so the dimensions is L. This is distance, so the dimensions is L. Let us now calculate the dimensions of this term. If we do that, the dimensions of v, which stands for velocity, is what? Lt minus 1. The dimensions of t is capital T. This guy takes care of this guy, and we end up with what? L. Numbers are dimensionless. So let's look at the dimension of this term. This will be Lt minus 2, and this will be T2, right? This and this takes care of each other, and we are left with what? L. So you realize that this term, and this term, all of them have the same what? Dimensions. As a result, this equation is correct. Let's look at the equation below. Now, let us look at the dimensions of this term. The dimension of mass is capital M. The dimensions of velocity squared is LT minus 1 all squared. So this will give us ml squared t minus 2. Let us look at the dimensions of this term. The dimensions of force is m, lt minus 2. If we multiply this by L, we are going to have what? It will boil down to ml squared t minus 2. Let us look at the dimensions of this term. I'm going to do that right here. The dimensions of g, which stands for acceleration, is L t minus 2. The dimensions of h, which stands for height, is L. So this will give us L squared t minus 2. Is this equal to this? Is this equal to this? This means that this equation is what? Incorrect. You understand that, right? That implies that this equation is incorrect. So we can use dimensional analysis to check for what? The correctness of an equation. Another use of dimensional analysis. Now, before we do one more example, let me clarify this. Let me clarify this. There is a distinction between units and dimensions. They are totally different things. Units and dimensions are totally different. A unit is a measure of a physical quantity and used to identify that physical quantity. The dimension of a physical quantity denotes the physical nature of that word, physical quantity. Even though a given physical quantity can be measured with different units, it has only one dimension. Therefore, you cannot use one in place of what? The other. It's absolutely critical that you understand that. I insist because there are some crappy videos on YouTube that will confuse you on this too. You get me, right? So don't fall for that. It will get you into trouble. Next, when an equation is all algebra, what do? You check for dimensions. But when numbers are inserted, what do? You check for what? Units. You check for units. I cannot overemphasize the importance of this sentence. When an equation is all algebra, you check for dimensions. But when numbers are inserted, you check for units. But when numbers are inserted, you check for what? Units. This statement helps you to know when units are important and when dimensions are important. Do you understand that? Now, all rules obeyed by dimensions also apply to what? Units. All rules obeyed by dimensions also apply to units. The third thing you need to bear in mind is numbers, angles are all unitless. Numbers, angles are all unitless. Let me add to the list trigonometric functions, logarithmic functions, exponential functions. These are all unitless. Do you understand that they are all unitless? Let me demonstrate with an example. If an equation is given that x is equal to alpha t plus beta t squared or let me just use half beta t squared, and you are asked to look for what is alpha and the beta, how will you know? In order to determine the identity of alpha and beta, you will use dimensional what? Analysis. We know that we can only add or subtract two terms only if they have what? The same dimensions. We can only add, subtract, or equate two or more terms with the same dimensions. Therefore, we can therefore say that the dimensions of x is equal to the dimensions of alpha t, which means that the dimensions of alpha will be equal to the dimensions of what? X divided by the dimensions of t. The dimensions of x is L. The dimensions of t is what? Capital T. What does this quantity? What is the quantity that you've seen today with the dimensions L over t? Velocity. So alpha represents what? Velocity. You see that, right? The dimensions will help you to identify a given physical quantity in an otherwise situation that you will not know. Now let's look on to beta. The dimensions of x is equal to the dimensions of beta t squared, which means that let me change the color, which means that the dimensions of beta is gonna be equal to the dimensions of x divided by the dimensions of t squared. This is L divided by t squared. What quantity is this?
Acceleration.
Acceleration. Do you see that? It's acceleration. Let me do another example again. Given that x is equal to a cosine omega t, what is the unit and dimension of a and omega? What is the unit and dimensions of a and omega? We can only equate two things with the same dimensions, right? We can only add or subtract two things with the same dimensions, right? Great. We also know that trigonometric functions are dimensionless. Are we together? What that means is that the dimensions of this quantity will be 0. What that implies is that the dimension of this quantity is 1. Let me put it that way. Therefore, the dimensions of omega t should be equal to 1, which means that the dimensions of omega will be equal to 1 divided by the dimensions of t. This is 1 over capital T, or t raised to the power minus 1. As a result, the unit of omega is what? Just seconds raised to the power minus 1. Do you feel me? Now the next, now look up everybody. Look up everybody. We can only equate two things with the same dimensions. So we have equated x with the quantity a This means that x dimensionally is equivalent to what? A. Do you get it? Therefore, the dimensions of x is equal to the dimensions of A, which is going to be equal to what? L. This means that A is measured in what? Meters. This implies that A is measured in meters. Let me do another example again. You are given that Q is equal to Q naught 1 minus E raised to the power negative alpha T. We really don't care about what Q and Q naught stands for. The question is, what is the unit of alpha? The trick to this question is that this exponential term is dimensionless. Do you get it? This exponential term is dimensionless. And for that to be dimensionless, it means that the dimension of alpha t is equal to 1, which means that the dimensions of alpha is equal to 1 divided by the dimensions of t, which is capital T raised to the power 1. You understand that, right? Which is capital T raised to the power 1. Let me do another example again. Yes, please.
Why, when the previous question, value of E was taken away?
Remember that this is a logarithm, an exponential function. And exponential functions are dimensionless. So E is almost like a number raised to a power something. Yes, please?
Is it unitless?
It's unitless.
And
Yeah, let me put it this way. Wait a minute, don't write yet. Don't write yet. It's a very good question. Very, very good question. Very good question. Anything, listen, anything that is unitless is dimensionless. But not everything that is dimensionless is unitless. In other words, if you don't have units, you don't have dimensions. But if you don't have dimensions, you can still have units. Simple example, when a baby is born and the name of the baby is not yet given, the baby still wears clothes, right? The clothes are the units. Without a name, you don't have dimension. You don't have an identity. Do you understand me? Your identity will always remain you. Dimension is the identity of a given physical quantity. I love that. The identity of a given physical quantity. That's a new one. So, it's possible, for example, if you are involved in a traumatic accident and you forget everything, you will still get up with dresses on your body, but then you don't have a name. You've lost your identity. So it's possible not to have a dimension, but to have what? A unit. Let me give you a physical example. Angles are dimensionless, but they have unit. An angle is measured in what? Radians. But are dimensionless because they are what? A ratio of what? Two quantities. Do you get me? Let me put it this way. If you have a circle, this angle theta, the radius of the circle is r. This is the arc length s. S is defined as r theta, which means that theta is going to be equal to s divided by r, right? So an angle is a ratio of what? Two lengths. Therefore, it's dimensionless. but angles are measured in what? Radians. Do you get me? Angles are measured in radians. Even though dimensionless, they still have units. Now, the units of dimensionless quantity, are pseudo units or pseudo units. Let me pronounce it right. Are pseudo units. Yes, you emailed me, right? Good. Good luck and be safe. All right. See you next week. Make sure you watch this video because the quiz is gonna be on, or the test.
What?
Yes, please.
Could you repeat the definition?
The units. Let me put it this way. The units of dimensionless quantities are called pseudo units. The units of dimensionless quantities are called pseudo units. The units of dimensionless quantities are called pseudo units. Another function of the principle of dimensional homogeneity is its ability to help us derive mathematical relationships between two or more physical quantities. Let me put it this way. We can use dimensional analysis to derive the relationship between two or more physical quantities without actually doing the concepts. In other words, dimensional analysis gives us the power of accurate estimation. Dimensional analysis gives us the power of accurate estimation. Let me explain, or by doing an example. When I was growing up, I loved the cartoon Tarzan. I don't know why. Tarzan hangs on a swing over a river with crocodiles, and he swings back and forth. But then you are here and you are curious as to what really are the factors that affect the number of oscillations Tarzan makes in 1 second. You really want to know, to accurately determine the period, the time it takes for Tarzan to what? To swing back and forth. And therefore, to do this, you have to look at the situation and to determine the variables that will possibly affect the period. We have what? The length of the rope. We have, we have the length of the rope. We have the mass of Tarzan. Because Tarzan is on Earth, we have the acceleration due to gravity. So possibly, the period of oscillation of that rope depends on the mass, the length, and the acceleration due to gravity. Now, in order for us to use the method of dimensions, what you need to put in mind is that T is proportional to m raised to the power x, L raised to the power y, and G raised to the power y, Z. Mathematically, to take away this proportionality sign, we insert what? A constant. So t will be equal to what? Our constant, m raised to the power x, l raised to the power y, and g raised to the power z. So, we have the dimensions of t will be equal to the dimensions of k multiplied by the dimensions of m raised to the power x multiplied by the dimensions of l raised to the power y multiplied by the dimensions of g raised to the power z. Yes, please?
I just wonder, before we convert them to the dimension, like the real dimension, how do we name
The x, y, z.
yeah, the one in the bracket, M, L, G, the bracket.
This.
Yeah.
This is the dimension of mass, the dimension of length, the dimension of acceleration due to gravity. Have I answered your question? Okay, good. So this will be like the dimensions of t is capital T. This is a numerical constant, so the dimension is what? 1. So the dimension of m is capital M, all raised to the power x. The dimension of L is capital L, all raised to the power y. And the dimensions of G is LT minus 2, all raised to the power z. We can further simplify this to be T equal to M raised to the power x, L raised to the power y plus z, and T raised to the power minus 2z. We see M here, we see L here, but we don't see any of those there. To remedy that situation, we can do something that is totally legit, but will help us. We can add an M there. When we do, it's raised to the power what? 0. Because anything raised to the power 0 is 1. We can add an L here and raise it to the power what? 0, because anything raised to the power 0 is 1. Now, if this equation is dimensionally correct, in other words, let me phrase the sentence this way. For this equation to be dimensionally correct, it means that the power of m must be equal. It means that the power of L must be what? Equal. And the power of what? T's must be the same, right? As a result, x will be equal to what? 0. Negative 2z will be equal to 1, which means that z is equal to negative 1 over what? 2. Therefore, y plus z will be equal to 0, which means that y is equal to what? Half. Beautifully, we can therefore write down t to be equal to k m raised to the power 0, L raised to the power half, and G raised to the power negative what? 1/2. Or we can represent t to be k raised to the power the square root of what? L over G. So you see that we have actually determined the period of oscillation of Tarzan without really having to deal with simple harmonic motion. Yes, please?
Wait, sorry, how did you get the LT minus 2?
You mean here,
Oh, there's like some.
here,
Oh, H LT minus 2 to the power of C.
here?
Okay, then.
G is acceleration. And we determined the dimension of acceleration to be LT minus 2, right? Great. How much time is left?
10 minutes.
Pardon? Great. Let's do another example on this concept to further. Your test, your quiz will be in 2 sections. Section 1, you will derive a formula, and section 2, you will experimentally verify if that formula works. Yes, please?
Are we gonna have like homework practice questions like that?
No. I will just do a video with more examples. But if you need practice for the preparation of the quiz, I can post a worksheet on Moodle. All right? Now, let me do this. Let's say we have you are in a roller coaster park and you are sitting in here and this thing is swinging around. It's swinging around. It has a certain speed v. Since it's a circle, there is a radius r. There is a tension T in the string, and definitely you have a mass. You were wondering how the tension in the string depends on these factors. So all you need to do is identify the factors. You have M, V, and the R. Are we together? So this means that T is equal to a constant M raised to the power X, V raised to the power Y, and R raised to the power Y, Z. Let's continue, please. So we want to determine the tension in the string that you will experience. This is actually an AP question. What if you cannot remember the formula? What if you are asked to derive the formula? What would you do? In this case, if you have forgotten the concept, then you can use dimensional analysis. You first evaluate the situation and find out the factors that will affect that particular variable. Then you hit on this. Therefore, the dimensions of t will be equal to the dimensions of what? M, all raised to the power x, the dimensions of v, all raised to the power y, and the dimensions of r, all raised to the power z. Tension is a force. Remember the second class? We talked about tension being a force, and we know that the dimensions of a force is what? ml t minus 2. This is going to be equal to m raised to the power x, L t minus 1 raised to the power y, and the L raised to the power y, z. So this would mean that ml t minus 2 is going to be equal to mx ly plus z t minus y. And our target would be to determine the values of x, y, and z. Automatically, you realize that this is raised to the power 1. This is raised to the power 1, right? Therefore, x is equal to 1. And automatically, you see that negative y is equal to negative 2, which means that y is equal to what? 2. Also, you see that y plus z should be equal to 1, and y is 2, which means that z will be negative 1. Are we together? Hence, the tension on the string can be written as m raised to the power 1, v raised to the power 2 divided by what? R. So you realize that you have derived the formula for the tension on the what? In the string. Yes, please.
Is K no longer included?
K is a numerical factor which is actually equal to 1. Yes, please.
How did you get it to be divided by R?
Because R is raised to the power -1. We have, so determine how the pressure exerted on this is a function of the mass of the object, G, rho, H. Because the object is of mass M. You can still remember the dimensions of pressure, right?
Force over area.
Yeah, what was it again?
MLT minus 2 over L squared, which is ML minus 1T.
So those are the dimensions of pressure. Everybody get to work, please. Work in your groups. All right, I just received an email from, how do you call these guys again? EdTech, the guys, ESCO. Yeah, they said they're looking into the problem. Oh, this is for Physics C, sorry. Please work in groups. Is this the end of the class?
Yes.
All right, this is your homework then.
So what's the
Rho is pressure density.
what is the question?
Determine the formula for pressure.
It's like,
All right, do you guys have a few minutes to spare? Let me do this problem for the sake of your quiz. It will take about a minute or two. Do you have a few minutes to spare? We'll write this P to be equal to, I will negate the constant mx, gy, rho z, h, I don't know, t. So this will be ml minus 1, t minus 2, all of this equal to mx multiplied by ly, t minus 2y multiplied by my dot minus 3, this is z, lt. So if you look at this keenly, 1 will be equal to what? X plus z, negative 1 will be equal to, for L, y minus 3z plus t, and negative 2 will be equal to negative 2y. You realize that you will determine y in this equation, which is 1. Substitute y in this equation, and then you will get a simultaneous equation in terms of what? X and t. And you will be able to solve for what? X and t, all right? So good luck, and I've given you enough hints. I hope something don't tell me to give